Welcome friends. In this session and coming sessions, I would like to explain some methods of finding numerical solution of ordinary differential equations. You may be familiar with the ordinary differential equation and the analytical methods of solving certain types of ordinary differential equations. All these methods can be applied to solve only a selected class of differential equations like variable separable equations, homogeneous differential equations, linear differential equations, etc. In many practical applications in the field of engineering and science, there arise many first order, first degree differential equations which cannot be solved analytically. In such cases, we shall go in for the numerical methods to solve them. We know that the general solution of a differential equation of the nth order has n arbitrary constants. Hence, to find the particular solution of an nth order differential equation, we require n conditions. Usually, these n conditions will be provided by the values of the dependent variable or its derivatives for n specific values of the independent variable. If all the n conditions are specified only for the initial value of x, that is the independent variable, then the problem is called an initial value problem. For example, the problem of solving the differential equation d square y by dx square is equal to f of x y dy by dx, subject to the conditions y of 0 is equal to a and y dash of 0 is equal to b. Then this problem is an initial value problem. If the conditions are specified for 2 or more values of x, then the problem is called a boundary value problem. For example, solving the differential equation y double dash of x, y double dash means d square y by dx square plus a of x into y dash of x, that is a of x into dy by dx plus b of x into y of x is equal to c of x, subject to the conditions y of x naught is equal to some k1 and y of x n is equal to some constant k2. This is a boundary value problem. Numerical solution of a differential equation satisfying the given initial or boundary conditions consists in finding the values y1, y2, y3, etc. of the dependent variable y corresponding to the equally spaced values x1, x2, etc. of the independent variable x, so that the pairs of values xi, yi, these are the pairs xi, yi, satisfy approximately a particular solution of the differential equation. A solution of this type is known as a point-wise solution. Point-wise solution. Various numerical methods are available for the solution of differential equations, but all of them lack the generality of the approach since they only give the particular solution corresponding to a given initial condition. This is a serious disadvantage because if solutions are required corresponding to several initial conditions, the entire numerical method must be repeated for each new case. Numerical solutions of differential equations are obtained in one of the following two forms. First one is an approximate series for y in ascending powers of x or x minus x naught, from which the values of y corresponding to specified values of x can be obtained by direct substitution, and second one is approximate values of y corresponding to only specified values of x. Here we shall discuss the Picard's iterative method for solving an initial value problem. Method is Picard's iterative method. Consider the first order differential equation of the form dy by dx is equal to f of x y, a function of x and y, such that y of x naught is equal to y naught. We want to solve this differential equation. First of all, we integrate both sides of this equation with respect to x between the limits x naught and x. That is, we can write integral from x naught to x dy by dx is equal to integral from x naught to x f of x comma y dx. That is, integral of dy by dx with respect to dx means y is equal to y naught plus integral from x naught to x f of x y dx as y of x is equal to y. Note that the required unknown, that is y, occurs inside of this integral and also outside in the same expression. Such an equation is called an integral equation. This is an integral equation. This can be solved by an iterative process, provided the integrations involved can be performed in successive steps. We also note that any solution of this equation is also a solution of the required differential equation with this initial condition. We assume that y naught as an initial approximation of y, that is y is equal to y naught. Initially we assume this and obtain a better approximation y1. We denote y1 for the approximation of y by replacing y in the integrand by y naught. We replace in this integrand f of x y with this y naught in order to get the better approximation y1. That is, we can write y1 as y naught plus integral from x naught to x f of x comma y naught dx. Now, the integrand, this integrand, that is f of x comma y naught, is a function of x alone, because y naught is a constant. Therefore, this is a function of x alone, and this can be integrated by the normal integration. The first approximation y1 thus obtained is substituted for y in the integrand and the integration performed, which gives a second approximation, namely y2. That is, y2 is equal to y naught plus integral from x naught to x f of x comma y1, the first approximation of y dx. Continuing in this manner, the nth approximation is given by the equation yn is equal to y naught plus integral from x naught to x f of x comma y n minus 1, that is the previous approximation dx. Y n minus 1 means the previous approximation of y. This formula is known as Picard's iteration formula. If f of x y is sufficiently regular near the point x naught y naught, we have y naught, y 1, y 2, that is the approximations of y will tend to a limiting function y of x over some interval about x is equal to x naught, which will satisfy both the differential equation and the initial conditions. This is the Picard's iterative method. First of all, we integrate on both sides with respect to x between the limits x naught and x. Then in this integrand, we put y is equal to y naught as an initial approximation, which will give a better approximation of y as y 1, which is y naught plus integral from x naught to x f of x comma y naught dx. Once we obtain a better approximation y 1, we use this y 1 for y in f of x y, and then integrate will give the second approximation as y 2. Continuing in this manner, we can write the nth approximation as y n is equal to y naught plus integral from x naught to x f of x y n minus 1 dx. This formula is known as the Picard's iterative formula. Using this method, we can solve this type of differential equations. Now, consider an example for solving a differential equation using this Picard's iterative method. Apply Picard's method to find the values of y at the points x is equal to 0.1, 0.2 and 0.3. Given that the differential equation dy by dx is equal to y minus x, such that y of 0 is equal to 2. We want to solve this differential equation for x is equal to 0.1, 0.2 and 0.3 by using the Picard's iterative method. We have the Picard's iterative formula y n is equal to y naught plus integral from x naught to x f of x y n minus 1 dx. This is Picard's iterative formula for the differential equation dy by dx is equal to f of x y, such that y of x naught is equal to y naught. In this problem, f of x y is y minus x. The given condition is y of 0 is equal to 2. That means, the value of y when x is equal to 0 is 2, that is y naught is 2. Taking this y naught equal to 2 as an initial approximation, then we get y 1, that is the first approximation, as y naught plus here y naught is 2 plus integral from x naught to x, here x naught is 0 Therefore, x naught to x means integral from 0 to x f of x y naught. F of x is f of x y is y minus x. Therefore, f of x comma y naught is equal to y naught minus x, that is here y naught is 2, that is 2 minus x. Therefore, we can write y 1 is equal to 2 plus integral from 0 to x 2 minus x dx. On integration, we get this 2 plus integral 2 dx means 2x minus integral x dx is x square by 2 between the limits 0 and x. That is equal to 2 plus, on applying this upper limit, we get 2x minus x square by 2. When x is equal to 0, when we apply this lower limit, these two terms will become 0. Therefore, we get y 1 as y 1 is equal to 2 plus 2x minus x square by 2. We write 2 factorial for 2 because 2 factorial is 2 itself. In a similar manner, this is our y 1. In this in a similar manner, we can write the second approximation y 2 as y naught plus integral from x naught to x, here x naught is 0 to x f of x y 1 dx, that is equal to y naught plus integral from 0 to x f of x comma y 1 is here 2 plus 2x minus x square by 2 factorial, 2 plus 2x minus x square by 2 factorial dx. This is equal to y naught plus integral from 0 to x. Our function is f of x y equal to y minus x, the y coordinate minus the x coordinate. Here the y coordinate is 2 plus 2x minus x square by 2 factorial. Therefore, we can write f of x comma 2 plus 2x minus x square by 2 factorial as 2 plus 2x minus x square by 2 factorial minus the x coordinate, that is minus x dx, which is equal to y naught plus, here y naught is 2 plus integral from 0 to x, here 2 plus 2x minus x means 1x minus x square by 2 factorial dx. This is equal to 2 plus, on integration we get 2 dx, integral 2 dx means 2x, integral x dx is x square by 2 minus 1 by 2 factorial into integral x square dx means x cube by 3. This is equal to 2 plus 2x plus x square by 2 factorial. Here in the denominator it is 2, we write 2 factorial for 2, that is x square by 2 factorial minus here 3 into 2 factorial means 3 factorial in the denominator, that is minus x cube divided by 3 factorial. This is the second approximation by 2. Similarly, the third approximation is y 3 is equal to y naught plus integral from x naught to x means integral from 0 to x, f of x comma y2 means the second approximation we already obtained dx, that is y naught plus integral from 0 to x f of x comma y2 is 2 plus 2x plus x square by 2 factorial minus x cube by 3 factorial dx. Our differential equation is dy by dx is equal to y minus x, that is f of x y is equal to y minus x. Therefore, we can write f of x comma 2 plus 2x plus x square by 2 factorial minus x cube by 3 factorial as y minus x means 2 plus 2x plus x square by 2 factorial minus x cube by 3 factorial minus the x coordinate y minus x, this is our f of x y. Therefore, we can write here this minus x dx. This is equal to y naught is 2 plus integral from 0 to x 2 plus 2x minus x is x plus x square by 2 factorial minus x cube by 3 factorial dx. This is equal to two plus integral 2 dx is 2x plus integral x is x dx is x square by 2 means 2 factorial plus here 1 by 2 factorial into integral x square dx is x cube by 3. We write 2 factorial into 3 in the denominator as 3 factorial, that is we can write this as x cube by 3 factorial minus integral x cube dx is x raised to 4 by 4 1 by 3 factorial into x raised to 4 by 4. Here in the denominator 4 into 3 factorial can be written as 4 factorial. Therefore, we can write this term as x raised to 4 divided by 4 factorial. This is the third approximation. The fourth approximation is y raised to 4 is equal to 2 plus 2x plus x square by 2 factorial plus x cube by 3 factorial plus x raised to 4 by 4 factorial minus x raised to 5 by 5 factorial. If we proceed in this manner, we can obtain the fourth approximation as y raised to 4 equal to y4 equal to 2 plus 2x plus x square by 2 factorial plus x cube by 3 factorial plus x raised to 4 by 4 factorial minus x raised to 5 divided by 5 factorial. Proceeding like this, after n plus 1 iterations, we can write y n plus 1 as 2 plus 2x plus x square by 2 factorial plus x cube by 3 factorial plus x raised to 4 by 4 factorial etc. plus x raised to n by n factorial x raised to n divided by n factorial minus x raised to n plus 1 divided by n plus 1 factorial. Now, putting x is equal to 0.1, 0.2 and 0.3, we get y of 0.1 as 2 plus 2x, here x is 0.1, plus x square by 2 factorial, that is 0.1 square divided by 2 factorial, plus x cube by 3 factorial, that is 0.1 cube divided by 3 factorial, plus x raised to 4 by 4 factorial, that is 0.1 raised to 4 by 4 factorial, plus etc. This is equal to 2 plus 2 into 0.1 means 0.2 plus 0.1 square means 0.01 divided by 2 factorial plus 0.1 cube by 3 factorial, that is 0.001 divided by 3 factorial is 6, plus 0.1 raised to 4, that is 0.0001 divided by 4 factorial is 24, plus next term is 0.1 raised to 5 divided by 5 factorial, that is 0.000, 4 zeros and 1 divided by 4 factorial, 5 factorial is 120, plus etc. This is approximately equal to, on simplification we will get 2.2052 approximately. This is the value of y at x is equal to 0.1. Similarly, y of 0.2, putting x is equal to 0.2, we get y of 0.2 as 2 plus, in this similar way we will get 2 plus 0.4 plus 0.04 divided by 2 plus 0.008 divided by 6 plus 0.0016 divided by 24 minus 0.00032 divided by 120 approximately. This is approximately equal to 2.4214. Here there is a correction, this term is negative, all the remaining terms will be neglected. Therefore, this is approximately equal to 2.2052. Similarly, y of 0.2 is equal to 2.4214 approximately, and y of 0.3 is equal to, putting x is equal to 0.3, we get y of 0.3 as 2 plus 0.6 plus 0.09 divided by 2 plus 0.027 divided by 6 plus 0.0081 divided by 24 minus 0.00243 divided by 120, which is approximately equal to 2.6498. That is, we substituted x is equal to 0.1, 0.2, 0.3 in the approximating polynomial y4. Then we obtained the values of the required values of y for the specified values of x. This is the Picard's iterative method. Now, let me conclude this session. In this session, we discussed the Picard's iterative method to solve an initial value problem of the form dy by dx is equal to f of x y such that y of x naught is equal to some constant y naught. Hope that you have understood this method. Thank you for watching the class. Have a nice day.